Okay, here we go. I tried starting this video once before without working through the problems, and it did not work out in my favor. But I've done them now. Sorry they're here so late. Hopefully we'll be able to get through this thing without any difficulty. Okay, so number one, we have a car. I'll draw it for you. A car. It's a Honda. Hello. And it's initially moving in the positive direction, and it slows to a stop. I'm not going to draw it as good this time. Hello. And it took 8.80 seconds to stop. And the distance from here to here was 126 meters. Okay, so the first thing it asks us is, what is the acceleration? Well, first of all, we can say it's going to be negative, because the car started with a positive velocity and ended at rest. Velocity final equals 0. We don't know what the initial velocity was. So, how do we find v initial? We can say, because acceleration is constant, we can say that the average velocity is equal to delta x, change in position, over delta time, how long it took. So this is like, 40 miles per hour or something, change in position over change in time. So we know delta x, x final minus x initial, and we know delta t. So average velocity is equal to 126 meters minus 0 meters over 8.80 seconds. And we plug this into our calculator and we get 14.3 meters per second. So, because acceleration is constant, we can say that v initial is equal to 2 times the average velocity. So velocity average, that's like saying how fast was the car going right in the middle, right when it was between starting and stopping. And because it's slowing down at a constant rate, however fast it was going here, halfway between its initial velocity and its final velocity of 0, its initial velocity is twice this value. So we plug this into our calculator, 2 times 14.3 meters per second, and we get 28.6 meters per second. So now we have initial velocity, and now using our kinematic equations, and being that we have every single variable except for a, we could use just about any kinematic equation we want to and solve for a. The fastest one would probably be a equals delta v over delta t. Very similar to the average velocity. And that means a is final velocity minus initial velocity over delta t, which would be final velocity is 0. Initial velocity is 28.6 divided by 8.80 seconds. And these are meters per second. I hope you can see this on the video. I'll try to write big. So with negative 28.6 meters per second over 8.8 seconds, we get negative 28.6 divided by 8.8, negative 3.25 meters per second squared. Acceleration. So that's it for the first part of that problem. The second part says if it took a force of negative 2,558 newtons to stop the car, what is the mass of the car? Now this is a good little question. What we do is say force is equal to mass times acceleration, right? Force, they give us that, negative 2,558 newtons, is equal to mass, which we're trying to find out, times acceleration, which we just figured out, 3.25 meters per second squared. So how do we isolate mass? We divide both sides by acceleration, giving us over negative 3.25 meters per second squared and we plug that right into our calculator. And we get a mass of 787 kilograms, which I think would be a pretty light car. So, I'll leave this, let me see, maybe I should bring it a little closer, make sure you get a good look at everything. Can you see it down here? I think you can see it down there. And we got the first problem done. No problem. Number 2. We have an airplane traveling from Birmingham to Chicago. Local, I like it. And that's a distance of 578 miles. And the speed of this airplane is 375 miles per hour. How long does it take for the plane to travel this distance? Well, let's see here. We have 578 miles. This is just a conversion problem, is all it is. You don't have to do any physics, you just have to. And in chemistry we call this stoichiometry, so if you want to look it up, how I'm doing it, you can Google that. It's called, dear Lord, maybe I'll spell this right. No, I think it's stoichiometry. Forget that I. 578 miles, and what we want to do is get miles to cancel out and just have hours left. And it travels, it's traveling at 375 miles per hour, but you could also write that the inverse way, 1 hour for every 375 miles. And you see that miles will cancel out, and we're left with 578 over 375 hours. We plug that into our calculator and we get 375, 1.54 hours. Good. Now let's move on. Oh, this is in the second part. So it wants to know the average speed of the airplane in meters per second. This is just more conversion. So we know it goes at 375 miles per hour. Let's see. Well, first of all, we can say this. There's 1 hour for every 3,600 seconds. And that's just 60 times 60. 60 minutes, 60 seconds each. I just happen to have that memorized. And what that's going to do is cancel out hours. And let's see, miles to meters. I don't know that off the top of my head. I may have to look it up here in a second. What I am going to do, I'm assuming he'll give you conversion units, like there's this many meters in or there's this many feet in a meter, or something like that. What I'm going to do is say that there's 5,280 feet, which I think is right, for for every 1 mile. And that's going to be, let's see here. Oh, and miles are going to cancel out, as you can see. So we're going to be left with feet per second. So 375 times 5,280. It's a big old number. And then we're going to divide that by 3,600. 3,600. And that's 550 feet per second. Now you want to get that into feet per second. You want to get that into meters, so what you need to do is figure out how many meters are in 1 foot. Or let's say 1 meter, because a foot's smaller, so I'll say 1 meter is how many feet. And I'll Google that right quick. I don't know it off the top of my head. It's 3 point something small, 3.1 or you probably already know this. I'm probably wasting my time. How many feet in a meter? Search. .28 feet. Wow, that's pretty big. Feet to cancel out. Let's say 550 divided by 3.28. So that's about 168 meters per second. And number 2 is all done. And if you want me to show you some more conversion like this, I'll be happy to do that. Maybe tomorrow I'll do another video if you want me to. So let's move on to number 3. You want to get a fresh sheet of paper for number 3? I do. Man, all this paper is real ugly. And so it's that. So number 3. A ball is dropped off a building 188 meters tall. So here's our building. It's a really tall building. It's a really skinny building too. And it is 188, I don't know if you can read that, but it says 188 meters. And we've got a ball. It's being dropped off this building. So we can say, I'll write it big, Y initial is 188 meters from the ground. And it wants to know how long it's going to take for the ball to hit the ground. So what is T? Well, obviously if it hits the ground, then y final must be 0. Do, 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 do. We know acceleration. It's negative g, which is negative 9.8. I don't know if he tells you 9.81 or 9.80. We always do 9.80. So if you use 9.81 and your answer comes out a little bit different than mine, then that's okay. Meters per second squared. The force of gravity, or the acceleration due to gravity. He wants to know how long does it take for this ball to reach the ground. Well, this is just kinematic equations. Y initial. Excuse me. Y final equals y initial plus. Are we going to be able to use this one? I don't. Oh yeah, we are, because it's starting from rest. So V initial is 0 meters per second. And I was wondering what was going on for a second there. Yeah, so anytime you have something being dropped or starting from rest, V initial is 0. And so that's V initial t plus 1/2 a t squared. This familiar old equation. So y final is 0. Y initial is 188. And sometimes people like to set y initial equal to 0 and y final negative 188. It's just another way you can do it. It doesn't really matter. Since v initial is 0 meters per second, this term is going away. Lucky us. Plus 1/2, and we know a, negative 9.8 meters per second squared. And all we're left with is this t squared. So we solve this algebraically. First off, we're trying to isolate t, so you want to get t's term on its side by itself first. So let's get rid of this negative, or this 188 meters, by subtracting it from both sides. When we subtract it from both sides, we'll end up with negative 108 meters over here equals 1/2 negative 9.8 meters per second squared t squared. Now let's get rid of this 1/2, and how we're going to do that is multiply both sides by 2. And let's see, 188 times 2. So we're going to get negative 376 meters equals negative 9.8 meters per second squared t squared. Now we just have to divide by gravity here. And when we do that, we get, I'll write it out, over negative 9.8 meters per second squared equals t squared. And those negatives are going to cancel out. That's good, because you can't have negative time. If you ever get a negative value for t, you know you've done something wrong, probably. Unless it's really advanced physics. 38.4 seconds squared equals t squared. And it's second squared because these m's cancel out, and this second squared here comes to the top because it's in a fraction in the denominator. Take the square root of both sides. Just going to write it like this. And we get t equals square root. And once again, if you get a slightly different number, like anything from probably 6.3 to 6.0, you're probably okay. T equals 6.19 seconds. So that's how long it takes what is the speed of the ball just before it hits the ground? Well, since we have linear motion here, linear motion with constant acceleration, we can say V average, probably getting a little crazy over here, is equal to delta x over delta t. And that's negative 188 meters, because x final is 0, x initial is 188, 0 minus 188, negative 188. And delta t, we just figured out, 6.19 seconds. Plug that into the calculator. .4 meters per second. Well, V final, oh, excuse me, it's negative 30.4. V final is 2 times V average. And it's going to be negative 60.8 meters per second. And that looks good to me. I don't have the answer key, so if I'm messing something up, we'll just have to figure it out later. Is that all you need in there? That's it. Number 4. Car moving around a curve. Uh-oh, we got a curve here. And I get to draw another car. Alright. From the top this time. It's not a pig in a blanket, it's a car. Has a speed 16.5 meters per second. Okay, and it has an acceleration of 3.20 meters per second squared. What it wants to know is, what is the radius well, fine, I'll put it in the uppercase R, it doesn't really matter. What is the radius? Well, for curves, we have a nifty equation that A, centripetal acceleration. Now the car experiences, here I've messed it up here, so all objects undergoing circular motion, that's my object, experience their acceleration towards the center of the curve, towards the center of a circle that they're going in. And we call that the acceleration. They're the centripetal acceleration. And their velocity is tangential to the curve. And that just means it forms a straight line with the outside of the curve. So V goes this way, and the radial velocity and acceleration goes in towards the curve. So that's what the centripetal acceleration, that's just for you to know, it's not really part of this problem. And it's equal to V squared over R. Well, we know this and we know this. All we need is this, which we can plug our stuff in and figure it out. Let's go ahead and do it actually. Let's go ahead and multiply both sides by R. And we're going to get R AC equals V squared. R is going to cancel out here. And let's divide both sides by A now to get R on a side by itself. So there's another equation you can work with. R equals v squared over a. Plug in what we know. 16.5 squared over 3.2. And it's time for our calculators. And we get 85.1 meters. You may get a little different answer, no big deal. Just as long as it's not too different. And I believe that is all we need. Oh, express the acceleration in kilometers per hour. We can do that. Well, the acceleration is, per hour squared. I was about to say, he's made a mistake. The acceleration is 3.20 meters per second squared. Right? So we'll call it 3.20 meters per second times second. Well, how many hours are in a second? There's seconds in an hour. There's 3,600 seconds in every hour. Right? But we only have 1 second here. Down here we have 2. So what we have to do, instead of just doing it once, forget this, 3.20 meters per second times 3,600 seconds per hour. We have to multiply it again to get rid of both seconds here in the denominator. See, this second will cancel out that one. This one will cancel out that one. And what that gives us is times 3,600 times 3,600. Let's see, how do I put this in the scientific notation? I don't know. It's going to be 1, 2, 3, 4, 5, 6, 7. 4.15 times 10 to the 7th. I'll write it down here. 4.15 times 10 to the 7th meters per hour. Squared. Sorry, because hour times hour. And I need a new sheet of paper. I'll use this one. So now that we have that, and this could really be done all in one step if you wanted to. Meters per hour squared times, okay, now how many meters are in a kilometer? 1 kilometer per 1,000 meters. Kilo is 1,000. So meters are going to cancel out. 4.15 times 10 to the 7th